These are the notes for the exponential growth unit that we're going to do. It's really just a one-day thing. Again, there's going to be a formula that I'm going to hesitate to have you memorize, and we're going to make sure you can create it. And so we're going to create it first, and then we'll go do a couple examples, and then due on Monday will be these notes, and then some of the work in the packet, which I'll talk about when I'm done with notes. So what we have here with exponential growth and when it occurs is when the rate of change, and remember we've talked about rate of change of some quantity, and this is going to be over time. Obviously these are going to be growth problems with real life applications. So over time it could be the rate of change of bacteria growth over time, or it could be the rate of change of temperature over time. But some quantity is going to be changing over time, and we generally call that dy dt. But our y here is going to be dependent upon what actually is changing. And when we do what's called directly proportional to y, you should have learned in Algebra 2 that when something's directly proportional, you multiply by a constant. When it's inversely proportional, we divide. So then it gives a couple examples of things that are directly proportional. And so right here we've got the gist of it, is that we say when something's directly proportional, or the rate of change over time is directly proportional to that quantity, we write the differential equation like this, where k is some constant. All right? So what this is going to cause is growth and sometimes decay. So we've done how to solve these, and I'm going to take you through it because, again, if you memorize instead of trying to create it, sometimes your memory fails. So you're going to want to know how to create it. So what we're going to do first is we're going to take that differential, okay, that change over time, that's proportional to the quantity. Oops, sorry, there should be a y here. And basically what I'm doing is solving this differential equation, which we've done quite a bit. It first involves separating your variables, so I'm going to divide both sides by y and multiply both sides by dt. And I've effectively separated the variables. And since I'm trying to solve it here for y, or for the quantity, so I can make a prediction what's going to happen later in time, I'm keeping my k over here. I mean, technically you could divide both sides by k, but again, when you're trying to isolate y, get everything else off onto the right-hand side. So then we integrate both sides, and we get the integral of 1 over y dy is the integral of the constant with respect to time. All right? And our integration laws tell us that the integral of 1 over y dy is ln of the absolute value of y, and the integral of a constant with respect to t would just be kt. And then again on both of those we have that plus a constant, so we've been putting that all on the right side. It says right here. All right? Next, because we're trying to solve for y, we need to do an inverse operation to get in there. And the inverse of the natural log is raising e to that power. So we've got e to the natural log is equal to e to the kt plus c. All right, so we write exponentially. Now this says drop the absolute value as e raised to any power is greater than 0. I really don't like the definition for why you're doing that. Really why you get to drop that absolute value is because when we get our y equal to, again, when I do e to the ln, it undoes it, and I get e to the kt plus c. And we've been writing that as e to the c. And really a better explanation for why those absolute values can be dropped is because this constant we can consider right now is plus or minus e to the c, so we can drop it on the left-hand side. And plus or minus a constant is still some constant. So I've split the right side into two factors, and it says e to the c is simply some constant. Sometimes on the side on the AP they'll go like this, where they'll introduce a new constant, maybe a, and they'll say it's plus or minus e to the c. But it's really not important in the grand scheme of the problem. So this is just some other constant which we've been calling large c. So what I've got here is y is equal to c e to the kt. So what I've got is I've solved for my quantity that's changing over time. And maybe it was bacteria, and I want to predict, well, what's going to happen in 24 hours. So you'll notice that I've got these two constants in here that are of concern, because if I want to use this to predict growth in the future, I need to know what those constants are, and then I can just plug a t in for time. Well, the first constant, this capital C, is very easy because really that is the quantity at time 0. Because you notice if I put a 0 in there for t, I end up with e to the 0, which is 1. So really what I get is y equals c at time 0. So when t is equal to 0, we just say y is equal to c. So what we've got going here basically is y is equal to, and a lot of times they'll call this constant the y value at time 0, e to the kt. All right? So this is your exponential growth model that we're going to be using when the rates of change are proportional. So let's go to the next page. Oops, I went too far here. Let's go to the next page here. So this is what I just derived for you, that when you have a rate of change that's directly proportional to some quantity y, we can translate that always into this form. And that you should really know. It says know this backwards and forwards, and instead of memorizing, I would say be able to create it in a pinch. So when we use it, I'm going to think when I do these, I'll do one example where I've kind of memorized it, and another where I'm going to assume that, well, maybe I forgot it, and how do I derive it? All right, so I want you to write this down. If we know dy dt, the rate of change of some quantity y, is directly proportional to that quantity y. Okay? When we solve that for y using the process on the previous page, we always will get this model, that the y is always going to be equal to some constant, and that constant is actually the starting quantity, which we're going to call y sub 0. Now, what I like to do with these word problems is whatever's changing over time, for example, if it were maybe temperature, then what I would do is I would say, well, d capital T dt is equal to k t. It's directly, maybe that's what's proportional. And what this would imply is that my temperature prediction is going to equal to the temperature at time 0, which means the starting temperature, e to the kt. I like to use these variables that go with my problem, like p for population or p for bacteria, that type of thing. I think it helps you sort out what you're doing. So the only unknown here is going to be this constant k, and we'll talk about how to figure out what that is in one of the next examples. So we're going to go through an example here, one with a punctured tire and then one with some bacteria, and I should have time to do both of them. So the first one says you run over a nail, and as the air leaks out of your tire, the rate of change in air pressure. So I would, since this is pressure, I would say dp dt. Rate of change in air pressure over time is directly proportional to that pressure. All right? That is my initial differential equation. So then it tells me, it states the fact that if the pressure, which is P, is 35 pounds per square inch and is decreasing at a rate, so again, this is decreasing at a rate of 0.28, which basically means they're giving me the negative 0.28, and they're telling me that the pressure is 35 pounds at that time. So really what they're trying to do is tell me what the K is. So if I go divide both sides by 35, I'm going to get K is about, shoot, I don't have my calculator here. There, negative 0.008. So they gave me enough information to solve for K. So my differential equation, I'm going to go back up here, is dP dt is equal to Kp. And again, the pressure change over time is directly proportional to the change of the pressure in the tire. Well, when it says solve that differential equation, I'm going to go back up to my model here and write down what I've got going. My pressure at any time is going to be equal to the pressure that it started at, and then E, right here, to the K, which I actually already solved for up above, T. Now I also know the pressure when I started, so I'm going to be able to even clean that up a little bit and replace this with 35. So I've got P is equal to 35 E to the negative 0.008 T. Well, now what I can do is use that growth model to determine what the pressure will be 10 minutes after the tire was punctured. This is very similar to the process you used to use when you would do the PERT formula in Algebra 2. This is the amount of money you started with. and then they would tell you the rate at which it's your money is accumulating interest, and they would tell you, well, figure out how much interest you have after, say, 10 years. This is a very similar process. We need the starting amount. We need to find this. They're going to tell us the time. So it's really similar. So my pressure after 10 seconds, 10 minutes, whatever, is going to be 35 e to the negative 0.008 t. And if you go do that on your calculator, you'll get about 32.309 pounds per square inch. All right? And it says that the car is safe to drive. Let me extend my page here. The car is safe to drive as long as the pressure is 12 psi or greater. So it says, for how long after the puncture will the car be safe to drive? Well, I need to know when is P going to equal 12 pounds per square inch. So let's go figure that out. I would have 12 equaling 35 e to the k, which I've already solved for, t. Now when I try to solve this for time, it goes back to, again, a pre-calc algebra 2 concept, where I'm going to divide both sides by 35, and my e is trapped up there, my time is trapped up there in an exponent. Well, how do I get up there? When I have e to a power, how do I undo that? I take the natural log of both sides. So I take the natural log of the left, and the natural log on the right is going to be ln e to the negative 0.008 t. Well, we have our property that says exponents come out front, and we know ln e is 1, and that's kind of why those undo each other. So what I get is the natural log of 12/35 is equal to negative 0.008 t. And on your calculator, if you then go take this quantity and divide it by negative 0.008, you're going to get about 133.805 minutes. All right, so I've got to cruise through here example 2, and then I will hopefully be able to finish this in the 3 minutes I have. So I have bacteria growing in a culture so that its rate of change, and I'm going to call that bacteria over time, is directly proportional to the number of bacteria present. That's my differential equation. It says solve it. Okay, well, I could take the long route, separate the variables, integrate, but what always happens is I'm going to get my bacteria is equal to the amount that I started with, e to the kt. Which means in order for me to predict the future with this, I need to know how much I started with. So they have to tell me what the bacteria present at time 0. I also have to go in and get k. So they're going to have to give me 2 pieces of information. Here's the first one. Initially, there's 5 million. Really what that is my b sub 0. If you go put 0 in for t, you're going to have 5 million equals b sub 0 times 1. So that b sub 0 is 5 million. So I've got b is equal to 5e to the kt. That's my first bit of information. Now the second bit. 3 hours later, it's grown to 7 million. Well, what that means is when I put in a 3 for time, I'm going to get a 7 million out for bacteria. So let's go do that. I get 7 million at time 3 hours later. So now I can go solve this for k, fairly straightforward. I divide both sides by 5. I take the natural log of both sides. Okay, this comes out front. ln e is 1. They basically undo each other. So I get the natural log of 7/5 is equal to 3 times k. And you'll notice it's very patternistic here. I've got the same thing I had when I solved for it last time. I get the natural log of the quotient divided by 3, and that's going to be my k. When I go do that on my graphing calculator, I believe you're going to get about 0.112. So let's write the whole model out. So what I've got, in order to be able to predict bacteria in the future, I've got the starting amount, which they gave me, e to the k, which I just found, times time. So any time in the future, I can now predict what the bacteria growth will be. And this says to graph it, but you guys have graphed exponential growth in other classes, so I'm going to do it really quick. We started off at 5 billion. This is time. This is bacteria after time. And we are here at 3. They said it was up to 7. And then you could go out to 10, and it's going to be very exponential growth model like this. So it says, what will the bacteria be 1 full day after the first measurement? Well, 1 full day, I'd go put in a 24 for t. It's very straightforward. Last up here, it says, well, when will it reach 1 billion?